Welcome to part B1. Hoping to do 2 videos on this one. There are 15 multiple choice questions. I usually find they're a little bit more tricky than the part A questions, but that could be a matter of, that could be pretty subjective. I'm actually not sure what the actual difference is. I know there's a difference, but I can't remember what it is. Let's just jump right in, okay? 36, got a gravitation question. As represented in the diagram below, an object of mass m located on the surface of the moon is attracted to the moon with a gravitational force F. That's what this is talking about right here. An object of mass 2m at an altitude equal to the moon's radius r above the surface of the moon is attracted to the moon with a gravitational force of, and it is our job to find that. It's talking about these 2 objects right here. First thing I want to do is I want to talk about, well, we know the mass of the second object is 2m. How far away is it? It says the altitude above the moon's radius, or above the surface of the moon, is equal to the moon's radius. When we use gravitation, we always talk about the centers of these objects. We want to know the distance between the centers. So if we've got one moon radius here, and then the distance from the surface to the object is another moon radius, that means that this distance is really 2r. So we have a mass that's twice as big as this one, at a distance from the center twice as big as it was previously. I'm going to show you how I prefer to do this question. Okay? It's a gravitation question. We cannot just use Fg equals mg here because we do not know little g for the moon. However, we do have some recourse. We do know this equation. Fg equals g m1 m2 over r squared. And I'm going to change this up just a little bit. Instead of m1 and m2, I'm going to do this. Fg equals g little m big M over r squared. And I'm going to come over here and define little m is the object, and big M is the mass of the moon. Little m is the mass of the object. Okay? Now, this works very, very well for the original object, okay, the object with a mass of m that's on the moon's surface. What I'm going to do is I'm going to make a description. I'm going to say, well, there should be another force, which I'm going to call Fg prime, just prime to denote that something is different, for the second pair of objects. We know big G is the universal gravitational constant. We know that the second object, M1, is a little bit different. M2, that's just going to end up being the mass of the moon. That's going to be exactly the same. And we know that the radius, the distance between the centers, excuse me, I don't mean to use the word radius. We know that that's going to be a little different. So everything that's going to be different, or could potentially be different, I marked with a little prime notation, okay? With a little dash. Now the nice thing about this is we know how much bigger the second object is, and we know how much bigger the second distance is. So I'm going to do this. G, since originally we were talking about an object with a mass of m, this one has a mass 2m, twice as big. I'm going to put 2m. The mass of the moon didn't change, so I'm going to use just regular old capital M there. And on the bottom, I have a distance between centers of 2r. And that whole thing needs to get squared. This is very, very important. If you had numbers to do this, if you had actual numbers that you were plugging in, think about it. You would double the radius first, or double the distance. I keep saying radius, I'm sorry. You would double the distance first, then you would square the whole thing. You would put the entire new distance in down here, then you would square it. You wouldn't square the old distance and then double it. That doesn't make any sense, okay? You have to take the entire new distance and square it. Now watch what happens with my algebra here. Fg prime equals, I'm going to pull this 2 out to the front, 2 big G little m big M over 2r whole thing squared is just 4r squared. And that squared is just attached to the r. Simplifying things, we get this. G little m big M over 2r squared. Take a look at this chunk right here. Does this look familiar to anyone? G little m big M over r squared. It is exactly the same as this, the original force of gravity. So what I could say is that the new force of gravity is equal to the original force of gravity divided by 2. Okay? This is a way to use algebra and be a little tricky to get an answer. Now, there's an alternative way to do this. You could plug in a whole bunch of numbers and make up the numbers and make sure that they work. That's fine. That is way too much work to me. And this will make your math skills better. Okay? It is a harder method, but please trust me, it does make your math skills better. Anyways, we see that the new gravitational force is half of the original. So therefore, it is not attracted as strongly. We get answer 3. Okay? That is a tricky question. Okay? So I think there's like 3 truly tricky questions that we've seen so far. And that's not to say that you should absolutely know all the other ones, but 3 that I really think require some pretty deep thought. Question 37. The graph below represents the relationship between velocity and time for an object moving along a straight line path. Okay? We have the velocity starts at -10, crosses through 0, and then increases this way as time goes on. What is the magnitude of the object's acceleration? The key here, we know that the acceleration is the slope of a velocity versus time graph. Or we should know that, okay? That's very important. The slope tells you the change in one quantity in terms of the other. If we have a v versus t graph, oh, there it is. If we have a v versus t graph, we want to know the slope tells us the change in velocity over time. That is literally the definition of acceleration. So all we need to do is take the slope. We need to find 2 points on the graph. We need to take you plug the coordinates for those points into the slope equation. The slope equation, if you forgot, is y2 minus y1 over x2 minus x1. Or in this case, let's be specific about our variables. What is the variable on the y-axis? Velocity. So I'm going to say v2 minus v1 over, x-axis is time, t2 minus t1. I just picked 2 points on here that are easy to read. You can pick whatever points you want, but please make them easy to read. Let's see, this is point 2, let's say. Velocity is 30, point 1, velocity is 10. So I get 30 meters per second minus 10 meters per second. Now I take the times, 4 seconds and 2 seconds. 4s minus 2s. Slope equals, let's see, 30 minus 10 is 20. 4 minus 2 is 2. 20 divided by 2. The slope is the acceleration, is 10 meters per second squared. That, again, is choice 3. That's a pretty simple question. The next one, we're going back to modern physics for a little bit, looks like. 2 muons would have a charge, a combined charge of what? This is a reference table question. No way around it. All we need to do is go to the reference table, look up muons. Muon is right here. They have charges that are equal to the charge of an electron. Okay? So -1e. If we have 2 of them, that would mean we have a charge of -2e. However, all of our answers are in coulombs. We know, let's see, muons are negative, so 3 and 4 don't make sense. We know 1 electron, if you look on the reference tables, I'll even go to it right now, 1 electron has a charge of, the same as an elementary charge, 1.6, where is it? 1.6 times 10 to the negative 19th C, okay? That would be 1 electron, would be negative 1.6 times 10 to the 19th C. If you have 2 electrons, it should be twice as much. Your answers must be 1, okay? If you didn't trust your math skills there, or didn't trust your abilities without actually doing some calculation, you could unit convert. You could set the unit conversion up. 1 elementary charge is equal to 1.6 times 10 to the negative 19th C. You get negative 3.2 times 10 to the negative 19th C. Still choice number 1. All right, 39. A 1.47, very good question. A 1.47 Newton baseball is dropped from a height of 10 meters, falls through the air to the ground. The kinetic energy of the ball is 12 joules the instant before the ball strikes the ground. The maximum amount of mechanical energy converted to internal energy during the fall is what? This is a very interesting question. Now, let's start from the beginning. 1.47 Newton baseball. What are they telling us here? They're telling us the weight, okay? they're telling us Fg, which is equal to mg. It's going to play a role later. It's dropped from a height of 10 meters. So let's actually get a little picture going. We've got a ball up here. Here's the ground. Here's where the ball is initially. And the ball is going to fall down towards the ground. Here's the final state of the ball. What we need to do is we need to determine what types of energy. We know it's going from here to down to here. We know we're talking about energy. Let's determine the types of energy that are present. Okay? And when we do that, we frame it by saying, well, it doesn't look like any work is being done. This seems like a closed system. It's very possible that the energy is conserved in this case. Okay? No work is being done by an outside force if we define our system large enough. So let's do ET equals ET. I'll even label this side the initial side. This side will be the final side. The ball let's talk about what types of energy there are initially. The ball starts 10 meters up. It says it's dropped, so let's assume it's not moving before it gets dropped. What type of energy would that be? Gravitational potential energy. P, E, G, and I'll put an I to remind us that this is initial, equals. The kinetic energy of the ball is 12 joules the instant before the ball starts to ground. So basically right when it's at the ground, the gravitational kinetic energy, the kinetic energy, the final kinetic energy. Now in a lot of cases you might just leave it there and say, oh, well they've got to be equal to one another. But let's actually try plugging this in right now. We're actually told the kinetic energy is 12, so let's just plug that in right now, 12 joules. The gravitational potential energy, we know the equation for this is mgh. Okay, we know it's mgh. We know mg already because we know that's 1.47 newtons. 1.47 newtons multiplied by the height of 10 meters equals 12 joules. Wait a second. If I write this out, I'm going to bring this over here, I would get 14.7 equals 12. That's obviously not true. Something else must be going on, okay? I forgot my internal energy term, okay? There must be some internal energy being, turned into internal energy here. We represent that with Q. And we can see from doing the math that Q is 2.7 joules here. So what this means is in the absence of that internal energy, if we didn't account for that, we would see that energy is not conserved here. But by including that in our analysis, we can still say that energy is conserved. Okay? It depends on how you're defining your system. In a lot of cases, let's say that friction maybe was negligible, you wouldn't have internal energy. But because there is air resistance, we see that not all of the initial potential energy becomes kinetic energy at the end. Therefore, there is a little bit that is left over that gets turned into internal energy. Okay, I'm changing my ideas on the fly here. I'm going to end with question number 40. I feel like this is going to take me a little bit of time to explain. And then we'll do 3 videos for this section. A projectile lands at the same height from which it was launched. Which initial velocity will result in the greatest horizontal displacement of the projectile? I usually represent this with dx. And I'm not going to, I could go through the equations, okay? I could do an AP level analysis of this, with some prompting, I could get you guys to do the same thing. It's not needed here, okay? There are ways of solving the question without going into that level of detail. We're going to look at situations that are similar to one another. We're going to look specifically at 1 and 2 together, and we're going to look at 3 and 4 together. Let's look at 1 and 2 first. We have particles or projectiles getting launched at the same angle, the same speed, 10 meters per second, 10 meters per second. One gets launched at 45 degrees, one gets launched at 30 degrees. A long time ago, we spent about a class period working out what the best, or talking about what the best angle to launch something at is. Turns out that it's 45 degrees. 45 degrees leads to the best balance between getting a projectile up in the air, so that it's in the air for a long period of time, and also still making sure that it moves forward relatively quickly. The x component of the velocity is relatively big. So it gets it up in the air a decent amount, so it stays in the air and can travel for a long time, and it also moves forward pretty quickly. Contrast that with 30 degrees. The 30-degree x component is going to be bigger, but if you only launch at 30 degrees, it's not going to be up in the air for as long. Okay? Therefore, this will actually go less far than choice number 1. Even though the x component is bigger, it's simply not going to be in the air for long enough. And we don't talk about what happens when it hits the ground, when it rolls or whatever. We just want the displacement to where it lands. Okay? So we know that 1 has to be bigger than 2, because 45 degrees, if we neglect friction and air resistance, is the ideal angle to launch something at. The same exact argument can be made for 3 and 4. We have initial velocities of 20 meters per second, but 3 has a launch angle of 45 degrees, 4 has a launch angle of 60 degrees. The 60-degree launch angle will get the projectile way up in the air, but think about the size of that x component. It's not going to be as big. It's not going to be moving forward as quick. You could go to an extreme. Think about launching at like 85 degrees. The x component's going to be tiny. It's barely going to move forward, but it's going to be in the air for a really long period of time. Okay? What happens again is 45 degrees is the best angle to launch from. And again, there are mathematical ways to prove this. I'm not going to get into them right now. Okay, 45 degrees, assuming everything else is the same, is the best angle to launch from. We have 3 will go farther than 4. So that means that we need to look at 1 and 3. We need to look at those two, 1 and 3. Now I think it becomes kind of common sense. You have 2 objects getting launched at 45 degrees. Which one's going to go farther? Kind of obviously it's the one you launch faster. Everything else being the same, launch angle being the same, the one you launch at a faster speed is going to go farther. The answer to this one is choice 3. I'll be back for the second part of our B-1 series.